So now we're going to look at two special triangles. These ones are going to be very useful for solving things without a calculator. So the first triangle we're going to look at is a 45, 45, 90 triangle. Now, a couple things you need to identify is that, first of all, this is an isosceles triangle. Because you have two equal angles, you will have two equal sides. We're also going to use the Pythagorean theorem to help us go through this proof and to come up with some numbers here. So what we're going to do is we're going to call this side 1 and 1 in length. Because they're the same, we can give them any numerical value, but why not use the easiest number, which is 1. What we want to do is figure out what is this side length equal to. So if we use the Pythagorean theorem, 1 squared plus 1 squared is going to equal our c squared. 1 plus 1 is going to equal c squared. 2 is going to equal c squared. And in order to get c by itself, we square root both sides. So the square root of 2 is going to equal our side c. So this special triangle has, every single time, it has these ratios between the sides. It's going to have a ratio of 1, 1, and root 2. Now if the sides were a little bit bigger, say they were 2, 2, then these things would also change. But the ratio between the sides would change by the multiple of a, whatever side length it was that you had in there. So these ratios will always reduce down to 1, 1, root 2 for this triangle. So this is very important to remember, and we're going to be using this a fair bit. Now our other special triangle is the 30, 60, 90 triangle. Now I've drawn this little dotted section here because it kind of relates to an equilateral triangle that has 60, 60, 60, 60, and we split it in half, which means that this side, this dotted side, and this whole side here are equal. Now we're not actually interested in the equilateral triangle because we're looking at right angle triangles. But if we split an equilateral triangle straight down the middle with a perpendicular bisector, this becomes half of this side length here. So if this whole thing was 2 and we divide it in half, it becomes 1, which means that this one is going to be 2. Technically this little imaginary side here is 2 and this would be a 1 here, so it's 2, 2, and 2. But again, we're not interested in the full 60 triangle, so let's get rid of all this. And now we're just going to use 1 and 2 and figure out what this side length is here. So again, using Pythagorean theorem, we can fill in, we have a 1 here, plus, this will be our b. Remember the two are a and b on the side, and the hypotenuse is c. We'll call it b squared is equal to 2 squared. 1 plus b squared is equal to 4. If we subtract 1 on both sides, b squared is going to equal to 3, square root both sides, and b is going to equal the square root of 3. So this side here is going to be root 3. Again, if we had any multiples of this, the ratios are still going to reduce down to this. So right here, this is quite important. The ratio of the sides and remembering these. So now we're going to look at the ratios for the special angles. I've written the two triangles down here for you for reference. 45-degree angles, we're going to have a 1, 1, root 2 for the ratio of their sides. The 30 degrees and the 60 degrees are going to have a 1, 2, root 3. And as a result, we can fill in this table and find exact values for each of these. Now again, if you need this, SOHCAHTOA. So if I'm looking at sine of 30 degrees, here's my 30 degrees. Don't forget you have to label the sides according to the angle that you're looking at. Hypotenuse will always be your hypotenuse. 30 degrees will have an opposite side here and an adjacent side here. So if I'm looking at the sine of 30 degrees, sine is opposite over hypotenuse, it's always going to have a ratio of 1 over 2. Cosine, adjacent over hypotenuse, root 3 over 2. And tangent is going to be your opposite over adjacent, 1 over root 3. If we look at the 45-degree angle, again, let's look at this one here, we need to label our triangle. Hypotenuse will always be the hypotenuse. This side here will be your opposite. This side here will be your adjacent for this particular 45-degree angle. Granted, 1 and 1 are the same, so no matter which way you do opposite, the opposite's always going to be 1, the adjacent's always going to be 1 for this triangle. So again, if I look at my sine, opposite over hypotenuse, 1 over root 2. Cosine is adjacent over hypotenuse, 1 over root 2 again. And your tangent is going to be opposite over adjacent, 1 over 1, which equals just 1. Now for the 60-degree angle, now we're going to have to relabel our triangle because we're looking at the 60-degree angle. So this side now becomes our opposite. This side now becomes our adjacent. Hypotenuse is always hypotenuse. So for sine of 60, opposite over hypotenuse, root 3 over 2. For sine, for cosine, adjacent over hypotenuse, 1 over 2. And for tangent, we have opposite over adjacent, 1 over root 3. Root 3 over 1, opposite over adjacent, which is just root 3. Now I wouldn't suggest trying to memorize the table because ultimately all you're doing is using SOHCAHTOA with these two triangles. I'd actually suggest remembering the triangles and using your SOHCAHTOA to apply them. So here are some examples of how we can use this. These would be non-calculator questions, especially on the provincial. These are things that you should know. Sine of 30 degrees, we would look at your 30-degree triangle, 1 over 2, and you're done. Cosine of 60, cosine adjacent over hypotenuse. And if I say tan of 45, opposite over adjacent, 1 over 1, so just 1. That's how quick it should be. You should know these triangles and know how to apply sine, cosine, and tangent to any of those angles to get those ratios quickly. Then you can look at harder calculations like these. Now sine of 30, we've already calculated that to be 1/2. So you can say 4 times 1/2 plus tan of 30. Now I haven't calculated that one yet, but here's my 30 degrees. Tan is opposite over adjacent, 1 over root 3. So you can plug that in. 4 times 1/2 is equal to 2 plus, remember 2 is the same as 2 over 1 times by 1 over root 3. So numerator with numerator, denominator with denominator, 2 over root 3. And you can leave it in that format. Here's another scenario. Sine of 45 degrees. Sine of 45 degrees, opposite hypotenuse, 1 over root 2. Cosine of 45 degrees, adjacent over hypotenuse, 1 over root 2. Minus. Now, 4 times cosine of 45. Well, cosine of 45, we've already figured that out. So 4 times 1 over root 2 all over 3. So now we have to work with our fractions and simplify this down. Now fraction times a fraction, numerator by numerator, denominator by denominator. 1 times 1 is 1. And root 2 times root 2 is the same thing as root 4, which is the same thing as 2. So that one's simplified. Minus, now remember, 4 over 1 is the same as 4, 1 over root 2, so it's 4 over root 2. All over 3. Now we don't want to leave these fractions over a fraction. So remember, 4 over root 2 times by, and remember it's 3 over 1, but when you're dividing, you take multiply by the reciprocal. So we have 1/2 minus 4/3 root 2. That leaves it in an exact format, not a decimal format, and you can do this without a calculator.